lecture. So today we have the last lecture, well, the last official lecture of the course here. And we are closing it out with light. So from last time, what we saw, we've got a sense of Faraday's law and Lenz's law. And that was basically saying, hey, if you have a loop of wire and you have some sort of changing magnetic flux going through that loop, you induce a potential, you induce a current, and you induce another magnetic field in that loop based on that change of flux. And the direction of those things is determined by Lenz's law, which is really not an equation. It's basically saying, hey, nature opposes change. Nature hates change. Nature doesn't want anything to do with change. If the flux is changing one way, nature opposes that change and induces a magnetic field against it. So I want to immediately jump into trying to get some use out of this thing. Oh, and you guys can't see those slides. There we go. Sorry about that. There's this slide that I was talking about, but it's stuff that we have seen from last time. Let's take a look at this problem here. It's a symbolic problem. Let's imagine I have some sort of rectangular loop, and it's near a wire that has some current going through it. We remember that a wire with a current going through it creates a magnetic field. But the main issue with this problem here is that the magnetic field that it creates is not uniform. It changes as you get farther away from the wire. So you have to think about that. What I want you to do here is go through this problem and think about what that's going to look like. Think about what the flux through my shape is going to look like. And then once you have that, find the induced current going through the loop. Let's assume that the current is changing with time. We don't necessarily know what it's changing like, but let's just say that it's changing as some di dt. That's my rate of change of the current. If you're finding a time derivative, that's the thing that changes. All right, squad. As a very strange thing, I'm having all sorts of issues with these things working properly today. I'll get rid of that real quick. Something's going on really weird. It's treating all of my pasted pictures as vectors, and I don't know why. I really don't know why. It's a brand new thing that I have never tried to put up with before. So, but it wouldn't be the last day of class if we didn't have some sort of issue technically to deal with. Right, it's the standard at this point. But let's go ahead and start taking a look at this thing. And now I'm doing my rogue tracing again as well. Cool. Okay. So I've got a length L, a width W, some initial distance away H, and we know that there is a current going through this thing. So first things first, I want to think about what is the magnetic field coming off of this wire. I'm going to do this in green to kind of match this color, or even better yet, let me steal this color. So the magnetic field coming off of this thing is going to look something like this, and these X's are extra bold for a reason. I use the right-hand rule to think about this direction. But the magnetic field is much stronger here than it is down here. As we go farther and farther away from the wire, the magnetic field decreases in strength. Right as B, I wanted that to be in green, please. B is equal, and I'll go ahead and write that out. This is B here. B is equal to mu naught I over 2 pi r. And real quick, these extra stray marks are driving me absolutely crazy. It's a sporadic issue that I don't have a solid answer for. But I have recently come up with the idea that if I remove the nib and put it back in, sometimes that helps it. We'll try that. Yeah, that's much better. Okay, so that's our expression for the magnetic field, and it's not constant over my space. Okay, well, let's talk about what the problem is itself, right? We know that we are looking for some sort of induced current in the loop. To find that induced current, we need to know what the induced potential looks like. Okay, well that's easy enough, but I need to find the potential first. I know that the potential, the induced potential in a loop, is based on the absolute value of the rate of change of magnetic flux. And that's a lot of words there, but we're looking for that magnetic flux. Now, I run into an issue here again, because what is my magnetic flux? I need to find that first before I can take a time derivative. So let's go with that. Let's say, okay, well, the magnetic flux, let me start with a true definition of this thing. So let me say the integral of B dot dA. First things first, can we all agree that the magnetic field is passing right through my surface? The B field, the A vector, they're both pointing in the exact same direction. There's no angle between them, right? It's not going through at some angle or anything else like that. The dot product is maximized. So I can get rid of that. Now the question comes up, and we already know the answer to this, but is B constant over all of A? No, it's not. I can't pull it out of the integral because it is not constant over A. What I can do, though, is I can think about what goes into A. If I'm thinking about the two different pieces, I have essentially some sort of X piece, some sort of Y piece. So let me do something like this. Let me say that the area of any piece would be X times Y, and then I would just have to think about, okay, well, what are the actual values that I have to plug in here? But then we look at these two things, and let's draw some little dots here. Let's imagine that I'm going along this line right here. Every single one of these tick marks. Is the magnetic field different on any of those points? Or is it the same for every single point that I just drew? What do we think? Any guesses? Yeah, that's the right kind of approach here. It's kind of jumping ahead a step here, but what we're seeing is that for any point that I've just drawn right here, every single little tiny tick mark has the exact same magnitude of the magnetic field, because the magnetic field doesn't care about where I'm at relative to the wire in the X direction. It cares about how far away I am from the wire itself. So that doesn't show up in the X direction, that shows up here along the Y direction. So then when I'm thinking about how does A change relative to B, I'm going to say, okay, well, the X is constant, and the X is really L. The Y does change with B. Or B changes with Y, rather. So when I'm talking about finding what dA actually is, I don't know how to integrate dA, but if I write that as L dy, with my bounds being right here and right here, now that's something I can integrate. So okay, then let me rewrite B while we're at it as well, right? Because we can see along any of these points, I could draw out my arrow R like this. So where's R really going back and forth between? Or let me rewrite this. Let me say, hey, this is my distance Y, right? As I've drawn it down here. So this really tells us what our two bounds are going to be. We have one bound, H. We have a second bound, H plus W. So let me go back to my integral then. Let me plug in some of these things that we just found. In black, please. Thank you. So I've got mu naught I over 2 pi, and I said I was going to replace it with y. I think it makes a little bit more sense to do that here. So I replace that with y times dA. dA is L dy. Now let me think about every single thing that might be changing with y. Mu naught, that's a constant. Is the current changing with y? No. The current of the wire is whatever the wire is, right? That's not anything to do with the B field. Well, I mean, it is to do with the B field, but it's not any sort of trick to go along spatially, right? The current is just going through this thing. It doesn't have a spatial dependence. The magnetic field, because of that current, does have spatial dependence. But I look at all these pieces and I say, hey, that can go out, that can go out, that can go out. All of these constants that I could pull out of this thing, mu naught I L over 2 pi, what's left inside is dy over y. And I said before, my bounds for this thing, I'm going from h to h plus w. Because we're going back and forth between those two. Those are easy enough to describe. I've got those. Those are two of my variables that I'm given in this problem. So I take this integral, and the integral of this just turns out to be a natural log. So mu naught IL over 2 pi times natural log of h plus w over h. Fantastic. Here is our final expression for the B field. Or rather, for the magnetic flux, is what I should be saying. B field was included in that. Here's my final expression for the magnetic flux, though. This has been a very, very long-winded way to get back to our original term. This isn't even our final step. But that's okay. Most of the hard work is done at this point, because we can take this expression back up. Now that we have a complete description of our magnetic flux, we say, okay, take that back up. Take a time derivative. Now I analyze this thing piece by piece. Mu naught, that's a constant. L, that's a constant. And I'm thinking, is this constant in time? Before, my question, was it constant in space? Right? And we pulled out all of these terms that were constant in space, and we left behind all the terms that were changing with space. Now we're saying, okay, we have figured out the space. Now we're thinking about what changes with time. And I am not scrunching up my loop. I'm not doing that in either direction, really. I'm not pulling the loop away. The loop is staying exactly where it was from before. The only thing that is changing with time is the current. So when I'm thinking about that time derivative, d dt of mu naught IL, I'm just going to go ahead and write all of this stuff out. Every single piece of this is constant except for the current. Time derivative attaches to the current and nothing else. So my final expression, for the potential at least, is di dt mu naught L over 2 pi natural log h plus w. So our very, very final step, now that we have the induced potential, I bring it back up to my original first equation. I take this expression, I divide it by r. And I want you to keep in mind here that I'm writing 2 pi r, but that is not 2 pi radius, that is 2 pi resistance. Big difference. And there we have it, our final expression. So now a question for everyone. What direction is the current going? Clockwise or counterclockwise? Start by thinking about the flux. What's going on with the flux? Is it going more or less into or out of the page? Yeah, it does depend on the changing current. I will give you that. That is very true. Let's assume that it's a positive change. If it was a positive change, if it's an increasing current. Yeah, excellent point, actually. Faster draw than me on that one. If it was a positively increasing current, what would happen to our flux? So in order of events here, if it was positively increasing, if that current that was coming from the wire was increasing, the flux goes more and more into the page. Lenz's law says nature hates that, wants to go the opposite direction. How do I create a magnetic field coming out of the page? I do so with a counterclockwise current. current. Let's not look at this one. Let's go ahead and look at this one right here. So this is very similar to what we've just seen, but it's a little bit different. It's a little bit different. So one of the things that might make this a little bit easier, let's go ahead and rename X real quick. And we'll see why. Let's sub in something else. Let's say instead of X, let's, I don't want highlighter. Let me call this instead, what's a good variable for length? Let's call this S. That might make this a little bit easier to solve for at first. So let's call it S for now. But it's a very similar problem to what we just saw, right? It's still a rectangle. It's still a wire producing our magnetic field. The big difference here is that instead of the current changing, the loop is getting pulled away. So I'll give you the hint here. Your steps for finding the flux are going to look extremely similar to what we just saw. But when we're talking about the change of flux, you've got to go through again and figure out which variables are changing and how are they changing. Okay, I think it's probably a good time to start looking at this thing. And again, this thing is going to make a vector on me, and I have no idea what to do about that. I used to call myself technically literate. I miss those days. But anyways, let's go ahead and label these things that are suddenly missing from this thing for no apparent reason. So I've got a velocity V, L, W. We said let's call this S instead. Now I'm going to draw my magnetic field as red this time to follow what we've got in the current, the external current at least, but in the same fashion as last time, right? It's strong here, and a little bit weaker over here. So hopefully that relative size is kind of apparent. But again, we know that what's going on here is that this magnetic field strength is not constant over the entire area. So it's not just a simple thing to solve out for. This time around, let's call this over X, for example. Right? Because if I'm thinking about my two directions, my radius R is really just X in this case. It's in the X direction. But anyways, let me go through the same steps as last time. Let me say, hey, if I can find just what that induced potential is, I would have my induced current. To find that induced potential, I would just need to take the absolute value of the time derivative of the magnetic flux. Again, I know it sounds very complicated, but it's really just one term. So then I need to find the magnetic flux. And we said before that this looks a lot like last time. So let me start with the full definition again. Let's not cut too many corners here. So it's B dot dA. Right off the bat, we can say, hey, isn't it true that the magnetic field lines are going directly through my surface? So the dot product should be, well, not vanishing, but maximized, right? The dot product cosine of 0 is equal to 1. So I'm left with the integral of B times dA, rather than B dot dA. That's just a little bit easier to solve. Now, I'm going to think about my space again. If I'm thinking about my area, if it had an X and a Y, now in this case, every point along L is constant for the magnetic field strength. So this time around, that's the one that's actually going to survive. dA is going to be L, a constant, times dx, because at every point in X, the magnetic field strength is different. So that's the variable that needs to be integrated over. Technically speaking, dA would go to dx dy. But integrating over y just gives us L, is what I should be saying with that one. But that's what we end up with. So I come over to this and I say, okay, fantastic. Now that I've got that, let me plug in all of these variables that I've got. Mu naught I over 2 pi x times L dx. And I look at my bounds this time around, and my bounds are from S to S plus W. With that in mind, I can pull out all of the constants, make this look a little bit prettier. And we have dx over x, which is just another natural log. So this will become mu naught IL over 2 pi times natural log of s plus w over s. And there's our expression now for the magnetic flux, which does look a little bit complicated, but it's very similar to what we just saw last time. Now, here's the point that's going to be a little bit different. Current is no longer changing. If we go back to the problem real quick, and let's stop all that stuff from showing up. A rectangular conducting loop of resistance R, distance away, yada, 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 yada. There's nothing in here about the current ever changing. There's nothing in here about me changing the width, or changing the length, or changing the resistance. Instead, what I'm doing is I'm taking this loop and I'm like dragging it away. Right? It's moving over across the screen like that. So in this case, what has changed? Which of all of these variables that we have left has actually changed? What do we think? To go from this state to this state over here. What changed with time? S, my initial distance away. Right, I could solve out for the flux of this state instead, but S would just be a little bit larger. How much does S actually change? If I let this thing go for 1 second, how much farther away would it be? What would the change of S be if I let it move for 1 second? Not B. Remember that B is going to be changing, but it's not something that's changing with time. It changes with space, but because the current is not changing, the magnetic field is actually going to be a constant here. You know, it is different for different parts of space, but it's not changing with time. Instead, if I let this thing go for 1 second, it would be V farther away. Right? My change of position in the x direction would be v times t. So then, when I'm thinking about this time derivative, the rate of change of s is the velocity given in the problem. So let's take that. Let's go back up with this thing. Let's say, okay, let's plug this in up here. What we're going to have then is, let me pull out the constants. We already determined that these values all together are not going to be modified at all, right? They're constant with time. So the derivative is going to skip right on by. So now I know my time derivative is going to be hitting s. So what I'm going to do, I'm going to simplify this a little bit. Let me go ahead and break this natural log up into 2 terms again. And remember that v is the velocity of the loop as it's moving away. So the natural log of s plus w minus the natural log of s. Take the time derivative of each of these terms. And here's where it's going to get a little bit funky. And we need to be careful with our calculus here. When I take that time derivative, so I need to do chain rule. Clearly, s depends on t. So I need to do chain rule. I'm going to end up first with the derivative of what I found in, or the derivative of the term itself. Then I multiply by the derivative of what I found inside. We already said w is a constant, but s changes with t. That is to say, ds dt is equal to v. But I'm left with, let me just go ahead and do the math out properly for now. So that's ds dt. Take the derivative of the function, chain rule, take the derivative of what's inside the function. minus 1 over s ds dt. Right, and this is not the same thing as taking a derivative of, if we were to take a derivative with respect to s, that would be a different story. Right, I want you to keep that in mind. When we're looking at a lot of these different parts, when we are thinking about if I were to take d ds of s, this would just be equal to 1. But if I were to take d dt of s, that's ds dt. Right, keep that in mind because this one over here ends up with ds over ds. So, and then remember, since w is a constant, the derivative of any constant is 0. So I'll take this step and I'll say, okay, fantastic. Let's combine everything together. My ds dt, this becomes v. This becomes v. Pull it to the outside. Now what's left in these brackets is going to be s times s plus w under, I would have, let's go ahead and write this thing out. So I would have s minus s plus w. I can simplify that by one more, and I can actually might as well do that. Let's cross out the s's. The w gets left. This term right here, I have to go back all the way to my beginning. Let's go ahead and wrap through like that. If I take that term now, I just need to divide by r to find my induced potential at the end of the day. And there we have it. Because the direction is determined by Lenz's law. So the extra negative signs floating around, we always just take an absolute value of this thing because the negative signs floating around will cause a little bit more confusion than they're worth. Lenz's law will tell us what the direction is. But yeah, good catch. I should have said that earlier. But since it's an absolute value, we can get rid of the negative sign. Well, for this next one, I know you guys are fried. So I'm going to go ahead and run through this one because it is a little bit strange. It's a little bit unlike a lot of what we've seen before. But let me give you the premise of this thing. We have some big, kind of like a croquet kind of shape here. And I've put this little bar that's allowed to slide back and forth on it. It has some mass. So it's going to fall, right? Gravity actually is an important factor here. But as it falls, it's going to be changing the magnetic flux going through this area up here. There are going to be some complicated things happening here, but what we're looking for is an expression for y of t. We want to find some sort of differential equation that describes what happens with our position y relative to how far we've fallen from the top. So I have to draw this one out, I realized last time, because the vector thing is really giving me grief this time around. So let's start by drawing this thing out, and I'm just going to run through this one. Go ahead and follow along, see what we can get out of it. But we've got something like this. Let me erase. Let's assume there's no bottom. It just kind of goes on forever. And then I'll have my bar going across. Kind of like this. Okay. Now I have this external magnetic field. Like that. And we defined a value y coming from the top down to where the bar is at now. So we got all these details. Okay. Oh, and there's a length L. We should not forget that. So I'm going to go through a lot of the same initial steps that I had from before, but this one is actually going to end up being a little bit easier. See, what's happening here is that because the bar has some mass, it is actually experiencing gravity, which is something we haven't had to think about for quite some time now, but it is experiencing gravity. As it falls, the flux through the main loop changes, induces a current. Things happen because of that. Let's get to that piece by piece. First, let me think about what's going on with that current. Let me start and solve it like I just have the last two. I promise, though, these steps are going to be the easiest one. It's towards the end that it's going to get a little bit strange. So we say, okay, well, same steps as before. Take the time derivative of the magnetic flux, all that good stuff. Magnetic flux. This is the easiest it's been yet. Because if I think about this integral, b dot dA, A will change with time, but the magnetic field as it goes through the area is the same the entire time. Right? B is uniform. So if B is uniform, then it's the same B going through every part of the area. This is the simplest we have seen this one yet. We can simplify this to just BA. And BA, in this case, is going to be B times L times Y. So now I take this expression. Oh, I wanted that in purple, please. I take this expression. Let me plug it in up here. Let me say, okay, let me take a time derivative now. Well, we've already said that the magnetic field is actually uniform and constant. Nothing is happening with that magnetic field. I'm also not scrunching up the loop as a whole. What's changing is that this gray bar is falling down. Y is changing with time. So when I'm thinking about that time derivative, how that time derivative hits the different pieces here. So let's do B, L, Y. B and L are both constants. But the Y gets caught. dy dt. And I'm going to leave it like this, but I do want us to know that dy dt, that is our classic definition of velocity. I'll even go ahead and write out that's velocity. Okay, so we know then that there is going to be an induced current going through this thing, and that induced current looks like this, BL over R dy dt. Now here's something. Let me think about what direction this current's going. Is my flux increasing or decreasing? What do we think? Yeah, the flux is increasing. Nature hates that. Nature hates that. Nature is going to want to try and oppose that. That means there is going to be an induced magnetic field coming out of the page. Be induced. What creates an induced magnetic field going that direction? My right-hand rule tells me that it better be rotating around counterclockwise. Now here's something. There's a current going through this bottom wire. What happens to a current in the presence of a magnetic field? Current in moving wire, ... What do we know about currents in wires in the presence of magnetic fields, specifically? They experience a magnetic force. And we need to think about this direction, right? Remember that the force goes as IL cross B. And remember that I do the vector over IL because it's really what direction is the current going? The current is going to the right. B is going into the page. My right-hand rule tells me then that the force points up, that there is an opposing force to gravity. As gravity pulls down, the magnetic force pulls back because nature hates change. So then I can say that the magnetic force, the magnitude of the magnetic force as I've got it drawn here is just going to be ILB because those things are perpendicular to each other, right? The cross product is maximized because the angle is 90 degrees. So with that in mind, now, assuming that there is not any sort of friction or air resistance, and let's just do ourselves a favor and assume that there's not, now we need to think about the kinematics that determine what's going to happen here. We're looking for what's going on with y and all of its derivatives. So what I can do is I can say, hey, take F net. F net is equal to ma, which I might recognize as, m times d squared y over dt squared, the second derivative of position, is equal, magnetic force is pulling me up, ILB, and that specifically is the induced current, which means that I shouldn't be writing I here, I should be writing my expression that I found before, BL over R dy dt. So this becomes B squared L squared over R dy dt minus mg. This is looking to be a nasty differential equation. I can write this out as m d squared y over dt squared minus b squared L squared over R dy dt plus mg is equal to 0. And this is as far as we're going to take this equation. I know some of you have taken some differential equations courses that would greatly assist in actually solving out what this thing should be, but it's not a tool set that I am expecting you to have mastered. It's not something that's going to be required for the course, but differential equations are ways of dealing with the fact that the acceleration is not constant. If you can describe what's going on, what plays into the acceleration, but the acceleration itself is not constant, all of our old kinematics equations don't work so well. You have to go to differential equations instead. And this is basically saying that a value's derivatives depend on the value, right? Which is not necessarily always true. Not for all the stuff that we have seen so far. So there are ways to solve this thing, but unless you have that toolkit, it's a little bit more complicated, and for the purposes of this course, this is good enough for us. But part B of this problem asks us to find, is there a terminal speed, and what is that terminal speed? So the first question can actually be answered by solving for V terminal. So let's just go ahead and do that. So my question for you guys then is, what is terminal velocity? What happens at terminal velocity? What's going on, and where do we draw the line and say this is the terminal velocity? What do we remember about that? Acceleration goes to 0. That's exactly right. We might remember this from things like skydiving and air resistance. You go fast to a certain point where the air resistance now counteracts gravity. You're still falling down, but your acceleration stops. So let's go ahead and do that. Let's say at terminal velocity, dy dt, which is really the velocity, is equal to v terminal. D squared y dt squared, the acceleration goes to 0. What does my expression do then? I would have 0 minus b squared L squared over R V terminal minus, plus mg is equal to 0. My terminal velocity, and indeed there is a terminal velocity, here's our proof, right? is going to be mgr divided by b squared L squared. And there we have it. This thing is going to fall until it reaches this speed. Which is a very fun thing, and this is an experiment that you can try and do yourself. It's not going to work perfectly, but you can get really, really close results with something very simple like this. Doesn't require any electronics or anything else. You just need a magnet and some wires. So there are very, very fun demos I have seen. We have a handheld one that works in the opposite way. It's a coil on a long tube here, and it creates an electromagnet beneath it. And when that suddenly turns on, the induced magnetic field shoots the coil out. It's a really fun thing. And it's a pretty simple one to build as well. There's some really cool stuff you can do with this. Okay, so in this problem, we've got a conducting loop. So we've got a circular loop that's essentially spinning around on axis, right, with a uniform magnetic field. And this one's going to be a little bit tricky at first. What I'm really going to recommend for solving this problem is actually going to be to draw this thing from a different perspective. Draw it from a top-down perspective and try and see if there's anything you can label on that would help you figure this one out. Now, if you've come back and given it an attempt, let's go ahead and take a look at this thing. First things first, let's go ahead and copy our picture over, and hopefully this doesn't give me too many other... Nope, it's doing the dumb vector thing again. All right, so we might have to draw in a couple extra details on this thing, but that's totally fine. I do want to have this thing just as a reference here before I dive all the way in with it. So we know that this thing has... oops. Let me get it set like this. There we go. Okay, so it's spinning around at an angular speed omega. So when I'm talking about taking this thing from a top-down view, this is from our side perspective. But if we take the top-down view, what do we see now? Well, from the top down, I don't see it as a circle anymore, really, right? I just see it as kind of a line like this. So there's my loop from my top-down perspective, and I've got my same magnetic field going through like this. But here's the big difference, because now what we can see is that there's an area to this, and it's coming out at an angle like this. This angle right here, theta, is the angle between A and B. We're going to take our easy version of the dot product, and we're going to use that to help us out here. So we are looking again for the induced current inside of this thing. So what I'm going to need to do here is I'm going to follow all the same steps as before. I want to start at the very end of the problem. I want to already have my induced current. I just need to find the potential. To find the potential, I just need to find the rate of change of the magnetic flux. So with all this in mind, now we just need to find that magnetic flux, and here is the trick. This one is actually not going to be so bad at first, but I need to leave like a theta behind just to make sure that we're not missing anything. So this would normally be integral b dot dA. Looking at this dot product, as we can see, there are going to be times where the angle between those two vectors is 0, but that's not all the time. So what I'm going to do is I'm going to try and go with like a general solution here. I'm going to say, hey, let me rewrite this. B dA cosine of theta. And with that cosine of theta, we've taken into account that we might not be at a 0 angle between these two pieces anymore. And that's going to be eternally helpful for dealing with what we've got in this problem here. But now what we're going to need to do, I need to think about this in a little bit of a different way. At any point, let me say I can start with any angle here, right? I can start whether we're completely aligned or not. If I finish this thing out, realistically, I know that the field is uniform through the entire area, even if it's some angle or anything else, right? The entire area, because it's a flat surface, it's going to be the same angle for all of the area. So integrating over that is really just the area of the circle. BA cosine of theta. Okay. Now here's a little bit of something. Now, if I'm looking at this thing, and do we have any idea of what, we don't have any sort of expression for what the radius actually is. We know it's circular, so we could say it's a pi r squared, but it's fine to just leave it as a for now. Now I'm thinking about this time derivative. B is constant, A is constant. Theta is changing. How is it changing? Well, we might remember here that if we're talking about angular position, then the first derivative of angular position, d theta dt, is equal to omega, our angular speed, that value that we're given in this problem. So now we take this expression. Let's carry it up to our last step. When we take that time derivative then, I'm going to have to do a chain rule here. So this is d dt of b a cosine of theta. Again, b and a are constants, so they come right to the outside. But now I have to do a chain rule. So first I do the derivative of the expression itself. Cosine becomes a negative sine of theta, and then I take the derivative of what's inside of the function. The derivative of theta, we see, is omega. So with that in mind, now here's another issue. Right, and before we get all the way through this thing, so we do have some expression here that we can use very much. But we run into a little bit of an issue in this case because clearly theta continues changing with time. I know that my current is going to be time dependent. But it would be nice if we could combine this thing and put it into terms that we know. Not necessarily putting it in terms of theta, but putting it in terms of omega. So what I can do here is I can say, hey, let me just pick a starting point. Technically speaking, I could say that my initial theta of t is equal to 0 is equal to whatever our initial position is, omega t plus whatever our initial position is, right? Phi naught. For the sake of the problem, let's just simplify this thing. Let me just assume that phi naught is 0. If I just assume that phi naught is 0, and it doesn't really matter because that depends on when we start the stopwatch, right? In either case, what we're really looking for is how does this current oscillate? So I can replace that in here. And then I'm also going to, while I'm here, take absolute value. Come back up into this expression right here. We got rid of the negative sign because we took the absolute value. Then my current BA over R times sine of, well, so here's another trick. Let me slow down before I make a mistake here. Sine is not the only thing. Or rather, the theta is not the only thing that might be negative here. Sine itself goes back and forth between 1 and negative 1. So if I'm looking for simply the magnitude of the current at any given point, I really have to not lose those absolute value signs. I really have to keep them around because sine is going to go back and forth between 1 and negative 1 the entire time. And then we have the omega here on the outside. That is just a positive value. But that's a little bit of a trick here. We do have to account for that. And now, realistically, I'm not going to fault anyone if you want to keep the negative sign in there or something else like that, because what we're seeing here, what I've got kind of listed down in the notes below for this slide, is that this is actually how we generate AC current. Right? The idea is that the current is not just going one way the entire time. The current is constantly going back and forth and back and forth and back and forth. Because it's constantly going back and forth, that's where we get, well, for one, if you've ever seen the lights flicker a little bit, if you are one of the people that might get headaches from lights flickering, that is an issue with fluorescent lights, that they oscillate at a rate of 60 hertz. So there is an almost imperceivable flicker to many lights. Incandescent lights, the old type of lights, don't have that because they're heat-based. So it doesn't get cold enough between times to really stop. So you don't see the flicker from incandescent lights, but fluorescent lights, you do see a flicker from them for that reason. That it's going back and forth the entire time. right? So if we want to just talk about the magnitude, it's proper to use the absolute value signs. But if you only are thinking about, if you really want to consider the fact that it's going back and forth, I'm not going to be upset if you ignore the absolute value signs and you leave them out. But that's what we've got. That's our final expression for the magnitude of the induced current at any point. So I do want to get through the rest of this material, though, because there's some really, really cool stuff that goes on in a lot of this. So we keep talking about this induced current and this induced potential. But if we think back to when we first started talking about wires, when we first started talking about what goes on, what actually moves current, what is current, what actually drives the current? What do we remember from that? What has to be there so that the electrons actually start moving somewhere? What gives them the push to go? Not necessarily a potential difference per se, but the potential difference implies an electric field. There's an electric field inside of the wire, and that's what moves the charge along. Right? So if we were to take some sort of classic loop just like this, and we go through and we solve all of this stuff, we find some increase of flux creates this current, but the current itself is being driven by an electric field. And even if we took away the wire, we have to assume that this would still happen regardless. So what we get here is that when you start changing magnetic flux, it's not just that it induces a potential, it's creating a circular electric field around where that flux is changing. Now, there is a really major difference between this and what we have seen so far. And I need to talk about that a little bit. When we're talking about a potential difference, it doesn't quite work in the same way as before, right? We might remember potential difference as if we had taken delta V is equal to the negative derivative E dot ds, right? And we had something like this, and this worked great, but it worked really great for radiating fields, or what we would call Coulomb fields, fields that come from point charges. Fields that are created by magnetic flux behave a little bit differently. For one, they're circular, all right? That's a pretty big difference. But this description of potential difference doesn't quite work so well anymore, not the same sense, because we get back to the same spot that we originally started in. Right, so this description is incomplete, to say the least. It still works for Coulomb fields and point charge fields, but it doesn't work so well for what we're talking about here. And in fact, if we're actually looking at a lot of these things, this was brought up a few different times. Some people have had some questions for me about where is the potential difference? How do I measure this on, like if I took a multimeter and I attached it to this circle, what would I see? And the answer is mostly nothing. And that's a little bit strange at first, but we have to think about it like this. Let me walk you through two different scenarios. So this loop has some resistance to it, right? Naturally, it's a wire that has some natural resistance. If I was to look at a very, very, very tiny section, I would have a very, very, very tiny amount of potential, but just because I've got that potential and just because there's a current going through this with a resistance, that section of wire dissipates that exact same amount of potential. So I end up with essentially no potential gained as I go across the entire thing, at least when we're thinking about circuits. Now, that's a little bit different if we think about AC generators and we say, hey, I know that AC electricity is in my house, and I know that AC generators look something like this. So what's happening then? Right? They have to be coming up with some sort of potential difference, some sort of voltage. It's a little bit different if we were to add a big resistor. If we were to add a big resistor, it's the same potential difference across the entire thing, right? The induced potential does not change. But now, where that's being dissipated is very different. It's no longer being evenly dissipated throughout the entire thing. And in fact, now over just this one resistor, I have almost all of my potential difference. Almost. Just a little bit less because the wires technically spend a little bit of that as well. But that's exactly what's going on. When we're talking about AC generators, there is essentially the coil itself that's generating the electricity, that it's experiencing the flux, but then it's attached to what we call a load resistance. And the load resistance is everything else running off of that. So everything else running off of that takes up the bulk of the resistance, and that's where the main potential difference actually is. So when we come back to this though, right now that we've had our kind of tangent on talking about potential difference, if we take this description, this idea that the magnetic field changing can create an electric field, well, there's some really neat effects that come out of this. Because this tells us that it doesn't just happen to wires, it happens to everywhere. And it interacts with everything that interacts with an electric field. And one of the big places this actually shows up is in eddy currents. So if you've done any sort of fishing or things on boats or anything else like that, you might have heard of this before, eddies or eddy currents. Generally, they're small, contained loops of flow. Right? The idea is that in an eddy current, we're not talking about from the left to the right is the entire flow. We're talking about essentially a contained flow, some sort of whirlpool or something like that. That's what an eddy current is. So let's imagine for a second that I've got some sort of magnetic field and I've got a copper plate and I try to pull through that copper plate. The flux through the copper plate is changing, right? Every space of that plate. Now, looking at the plate as a whole, that's a little bit different, but we can say that every single little part of the plate is experiencing a change of the flux. And because it's experiencing a change of the flux, it has an electric field over it. And because there's an electric field over it, it's generating current. And because it's generating current, the magnetic field is acting on the current and it pulls back. And that's a really fascinating thing. It's super cool to see. You can try this yourself. If you have some sort of non-magnetic material, you can see it tugs back. It's got a little bit of resistance to it. And it will never pull it back the other way. Because remember, it depends on you moving it to create that tug back in the first place. But it hates change. It wants to stop you from changing what's already there. So I really can't recommend enough. I've got it up in Dr. Alexander's lecture. There is a demo that we would normally run in person. But it's you can also look it up online, dropping a magnet through a copper pipe. This demo is fascinating. It is one of my absolute favorites. I love it. You can watch this thing happen in real time, and it is incredible. It is super cool. I know I've talked about it a little bit before, but it's a super cool one. Watch the Dr. Alexander's version of the lecture. I think it's about halfway through is when it starts. Find some different videos on YouTube. I unfortunately don't have enough money to just afford buying giant copper pipes and magnets, so I don't have that at home with me right now. But look up some demos of this thing because it is incredible. All right, so I would like to start talking about 30-9. This is our last whiteboard problem of the course. We have been through so many at this point, but this is our very final one. So what we've got here is some sort of solenoid, and we are going to use what we just saw about induced electric fields from Faraday's law. So what we've got, from a solenoid, we know that this is a pretty regular, consistent magnetic field, right? We know that. But what we can say is that the magnetic flux passing through that area is going to be giving us an induced electric field. So what we're going to need to do here is I want to take a side profile view of this thing. I'm not actually going to take this picture. I don't think it's particularly useful. What I'm going to do is I'm going to draw out a new picture here. So let's draw this big loop, and this is where the electron is. So let me place that real quick. Here is my electron. Inside of this loop, this is where we have our actual solenoid. And let's pretend for a little bit that that's actually all centered up. But this is where our solenoid actually is. And that's a really important distinction because ideal solenoids, remember, don't have magnetic fields outside of them. If it's infinitely long, then the magnetic field is purely on the inside. So I'm imagining here that I've got some sort of magnetic field because of this solenoid that looks something like this. But now I'm going to need to write out what we just saw with that equation. So that is to say the electric field around a closed loop. Electric field around a closed loop, E dot ds, is equal to the negative, because nature hates change, time derivative of the flux through that same loop, right? And that's the key here. It's kind of like when we were doing Gauss's law and everything else like that. We need to look at what is the flux contained inside of my big loop. So as I take this thing, I'm not going to use the entire area of my massive loop. I'm only going to be taking the area that actually contains a magnetic field. So let me have my two radii here. Let me say radius in black is going to be 10 centimeters. My radius in orange is going to be 5 centimeters. So I know not at all drawn to scale, but nothing ever is in this course anyways. Now, we are given a couple other details about this thing that we should keep with us. We know that it is 50 centimeters long. It's got 200 turns. So L is equal to 0.5 meters. N is equal to 200 turns. We know that there is a current passing through it, or specifically that the rate of change of current, di dt, is 0.5 amps per second. So I'm going to take that kind of same idea that I had before when I had some sort of increasing current in the exact same way, right? We're going to solve this out symbolically and plug in our numbers at the very end of the day. So I'm going to make a couple different arguments here. Let me start by solving out for what this flux should be. So if I'm looking at that flux in the first place, really what I'm looking at here is the circle, and it's got a uniform field going through the entire time, right? The field is going directly through my surface. There's no angle between those two. So really, this is just going to come out to be B times pi, and I'll do this one in orange, squared. So we know that that is the radius of the solenoid, right? Because the field isn't out in this area. The field is only contained inside the solenoid itself. So that is going to be, well, and I'm missing one more. Well, no, that's good. That's good. That's exactly what we need. The number of turns doesn't come into play here. And that's, I caught myself for a minute there. The number of turns doesn't play into the same way here because before when we were thinking about the flux going through some sort of coil, that was how many times is it going through the coil. Here, our coil is just this one black loop going around. So the turns don't actually matter for when we're talking about the flux anymore. The turns are being used to generate the magnetic field. The loop that flux is going through is just a single loop. So keep that in mind. So that is my result of what's going on with my flux, but I don't have an expression for my B field. So what I'm going to need to do is I'm going to need to plug in what do I have for a solenoid. A solenoid has a very regular magnetic field. Specifically here, it is going to be mu naught capital N I over L times pi, and then again, R squared. Perfect. This is all we have, right? This is down to almost all of our variables except di dt. We'll get back to that in just a second. Now that we have this expression for the flux, now we look at this equation, we say, hey, now we need a time derivative of what we have just found. Negative d dt of this integral is equal to negative d dt of mu naught n I over L pi r squared. The only thing that changes with time is the current. The number of loops of the solenoid doesn't change. Mu naught is a constant, L is certainly not changing, R is not changing. The only thing that's changing is I, so that picks up that derivative. And we're in luck here because di dt is actually a quantity that we do have. Remember, di dt was that negative, or the, not negative, it was the 0.5 amps per second that was given to us in the problem. So we've got negative di dt, mu naught capital N over L times pi r squared. Perfect. So that is the right side of the equation taken care of. Now, what is this left side trying to tell us? Or how can we use this? You might notice here that as I've drawn this thing, not super well, but I've tried to draw this in such a way that everything is concentric, right? It shares the same middle point. It is symmetric radially. And that was on purpose. Because keep in mind here that if we are matching some sort of symmetry, then all of the fields that we're expecting to see should also match that symmetry. We know that the electric field created by this change of flux is going to be going in a circular direction. So if we're thinking about that circular direction that might be created here, we expect that it's going to be aligned with the center of the axis of the solenoid in the first place. So as the thing is changing, the electric field that we expect to find, I need to think about what's going on here. I need to treat this kind of like as if there's a wire for a little while, right? If the flux is increasing and it's going more and more and more that way, then I'm expecting nature to oppose that, to induce a magnetic field coming out of the page instead. Here is my B induced. What creates a B induced? That way a current, following the right-hand rule, wrapping around counterclockwise. A current wrapping around counterclockwise would be because of an electric field wrapping around counterclockwise. So I could say that my electric field wraps around this circle, just like this. And again, we're following this symmetry argument, and that's a very important point, because when we start following that symmetry argument, finding this integral, what we've got on the left side of the equation, becomes simple. So simple. All it really comes out to be, we know that the electric field is constant over the entire circle. E dot ds, that dot product, we can see that the electric field is always going along the circle. We can also see that it should be uniform around the circle. Right? If we change radii, if we go here or here, of course that's going to change, but since we are going around one circle that is concentric with everything else, this simplifies to E times 2 pi r, and this is the radius of the loop. That's why r is in black, the 10 centimeters. So let's put these terms together at the very end. E 2 pi r is equal to negative di dt mu naught n over L pi orange r. Oh, I asked for that to be an orange, please. Orange r squared. So, part of this is a little bit weird because I have already found the direction. The direction would normally be determined by that negative sign. Since I have found the direction already, I would actually much prefer to take an absolute value here. But the negative sign does tell us about the direction if we're thinking about this in terms of if we're actually keeping track of where all the vectors are going. If we're actually keeping track of where all the vectors are going, the negative sign matters. So let's just say only concerned with magnitude. Direction already determined. That's all the negative sign would be doing. It would be telling us about the direction, but because we're kind of being a little bit loose with our vector notation anyways, I feel like it's better to just go ahead and take the absolute value of everything. Let's just worry about the magnitude. So when I do that, I'm solving out for the electric field. E is equal to, I need to divide by 2 pi, so the pi's are going to cancel out. I'm going to have di dt times mu naught n orange r squared divided by 2L. And that's, 2L R, black R. And now we have all of these quantities. Mu naught is a constant, n is 200, orange R is 5 centimeters, black R is 10 centimeters, L is 0.5 meters, and we know di dt is 0.5 amps per second. When we plug all of these quantities in, we should find an electric field of 6.283 times 10 to the negative fifth. And I want you to think about that value for a second here, because what we have just found is a very weak electric field. Right? Realistically, while an electric field is being created here, it is a really weak electric field. And this is why the effects are not super profound. They are pretty weak. As compared to, at least our single-digit electric fields that we have often seen. But something this small is very, 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 very tiny. But build up over enough time, you can start to have a few issues because of this. Right? This is like one of those low noise values that sometimes floats around in circuits and causes some issues sometimes. But that's not the end of the problem. The last thing we need to do is we're asked for the magnitude of the acceleration of the electron. Asking about that magnitude, we can say, okay, well, there is an electric field. That electric field creates an electric force on the order of Q times E, which is equal to the mass times the acceleration of the electron. The mass of the electron is a given value. The charge of the electron is another given value. We have the electric field. Plug in all those numbers together, we should find that the acceleration is 1.103 times 10 to the 7th meters per second squared. And that's it for that problem. The last whiteboard of the semester. So the last thing that we have, and this probably is not a huge surprise, but what we can do is we can take what we know from the Coulomb law and from the magnetic force, and we can combine that together into one force equation. And we call this the Lorentz force, and it's the combined electromagnetic force, right? This is actually how it acts on different point charges. A little bit of history. So James Maxwell, the person that I keep talking about Maxwell's equations and all of that good stuff, I know I've talked about this before, but in a historical kind of perspective here, electricity and magnetism, we had a lot of equations that described what was going on with each one, but it was not a complete system yet. It wasn't until Maxwell came in and kind of pulled together these different equations and said, hey, I think these are all related in some special way. I think there's something here that we're missing, something that we could do to tie it all together just a little bit better. And at the time, they were called the field equations, because this is really where we were talking about different fields. Especially Faraday's kind of view of fields was working just like this. But there was something a little bit strange, because if we go in order here, let's start with Gauss's law. This is our old favorite, right? Gauss's law said, hey, charges create electric fields. Yes, we know that. Then we said, okay, well, Gauss's law for magnetic fields says, hey, there is no such thing as a magnetic charge. It doesn't exist, right? Magnetic fields always come from dipoles. There's always magnetic dipoles. There's never magnetic monopoles. And we had Ampere's law, which said, hey, you can find a magnetic field because it's generated by current, by moving charge. And then finally, Faraday's law tells us that an electric field is created by a changing magnetic field. But there's kind of an asymmetry between these equations. Because if I think about this, okay, well, no magnetic monopoles, whatever. But I've got two equations that describe what can make the fields. I've got a creation of electric fields from magnetic fields, but can I make magnetic fields from electric fields? I don't know. Right? Because I through doesn't actually tell me that. I through just says a moving charge will create a magnetic field, but it doesn't necessarily imply that it's the electric field doing that. But at this time, there was actually another issue. We had some other issue going on here, and that's we couldn't describe what was going on with capacitors. We had set up a lot of different capacitors, and we found that when you turn on the switch and you start charging a capacitor, it creates a magnetic field. But this law right here, Ampere's law, tells us that the current has to be going through. So where's the current? It can't travel between the plates of the capacitor. That's the entire point of the capacitor, is that the current doesn't travel between those two. So something was wrong here, right? We didn't have a complete picture because this description, Ampere's law, worked for almost everything, but it didn't work for capacitors, which seems like kind of a basic thing to have an issue with, but we didn't understand it at the time. But Maxwell came in and he said, no, I've got this. If I look at the different pieces here, if I take one surface versus another surface, what we see here is that we should be describing mostly the same thing. Right? It doesn't matter how I draw this thing, I still see the same magnetic field either way. But if I draw the outside surface, S2, no current passes through it, but I still see the same magnetic field. So what we're missing here is what's happening to that current, what happens to that charge. And our solution to it was what we call the displacement current. The displacement current is describing the current that should be going through the capacitor, that we see going into the capacitor, but might not necessarily be going between the plates. And this is a really important point, right? Because it's not necessarily that we're looking at the displacement current. We know that the displacement current is the same as the current going into a charging capacitor, right? That's the same quantity. But what's happening here is this term displacement current is really a change of the electric flux. And with that, we have completed Maxwell's equations, right? This was Maxwell's contribution that really settled this thing and unified it all together to the point that we now say that electromagnetism is a complete field, right? Even if gravity's messed up and quantum mechanics is weird and wonky and general relativity is a solving nightmare, we're very confident in our description of electromagnetism. And now, because he brought them all together and made the necessary corrections, for one, the law is now called the Ampere-Maxwell law, but for two, we call the field equations now Maxwell's equations. And these four equations, along with a Lorentz force, describe everything in electromagnetism. Or almost everything. Very nearly every single thing we can do in electromagnetism can be done with these five equations. And it's pretty incredible, right? When you're talking about like unifying a field, 5 equations gives you everything you need to know. Even if you have weird things going on like dielectrics or anything else, the refractive index can be described by Maxwell's laws. Or Maxwell's equations, rather. All of it gets wrapped up in one beautiful package. And with this, you have classical physics. This entire year of material has been all leading up to completing what we call classical physics. Classical mechanics, thermodynamics, electromagnetism. Those are the 3 big pieces that make up classical physics, and up until 100 years ago, we would have said this is the complete picture of the world. This is all there is to know about physics. This is how the world works. About 100 years ago, partially because of these equations right here, things got a little bit more messy. Quantum mechanics and relativity popped up as brand new fields, and they showed us that our understanding was very incomplete. And I don't want to say any of this stuff as if these things that we have just spent the last year learning are worthless. They are very much not worthless. They are still taught to our majors. We have a 400 level course and often a 600 level course for each of these topics. Right? These are not fields that are useless. What these are very accurate descriptions of what goes on in most of the world as we know it. Quantum mechanics and general relativity are more accurate pictures, albeit much more difficult pictures of what reality is doing. So most of the time, classical mechanics is still extremely useful because it describes how the world works without getting super complicated. It's still reasonable systems to solve, and we still use it constantly. Right? I imagine that probably most of you will not have to do anything with relativity. On a rare occasion, you might. On a rare occasion, you might have to do something with quantum mechanics. And I realize now both of those are advancing to the point that they're becoming more and more common as time goes on. But classical physics is enough to deal with most of what you're going to have to live with. And that's going to get you 99.9% of the way there. And most of the time, that's good enough. It's only in very rare cases that we actually have to consider, the little cracks in the wall when we're thinking about physics. So congratulations. You've made it all the way through. This is it. You've gotten your basic view of everything that classical physics has to offer. Now, there are a couple more things that I do want to say on this, right? And a really big part of this is, for one, this is one way that we can write out Maxwell's equations. There is another way to do it. This is called the integral form of Maxwell's equations, but there is also a derivative form of Maxwell's equations, and it's trying to describe the exact same thing. So there's kind of a parallel equation for each one of these terms. What this turns into is we need to learn a couple things really, really, really fast here. We might remember our good friend del, right? Which is really just a derivative with direction. So del dotted with another vector, we might remember gradient. The gradient of potential gave us electric field, right? That was one use of del. Now there's another one where we dot it with a vector, and in doing that, that is called the divergence, and that is telling me how much if I'm moving out of a space. Right? That's really what it is. So if I'm thinking about some sort of charge or anything else like that, that has high divergence because the electric field goes out from the point charge. And that's exactly what this equation is trying to say at the top. The second one that we've got is the exact same thing, but for the magnetic field. And that says, hey, you can't have divergence in the magnetic field because, again, you can't have magnetic monopoles. The loops always come back around. So divergence is not a thing that you can have. Curl is a little bit different, but curl is telling me how much do I wrap around? How circular is this thing? And we can take the curl and rewrite some of these equations just as well. This down here tells us that the curl of the electric field is determined by the magnetic field, right? That's the circular electric field is generated by a changing magnetic field. And just in the exact same way, a magnetic field is created by a changing electric field or from a moving charge. So with all of these together, though, there are certain solutions. Let's imagine a scenario where we don't have charge. Let's imagine no charge. But let's think about what possible solutions we could have to these wave equations. Let's assume that there's still some sort of electromagnetism going on in some way that satisfies all four of those equations. Well, one of the solutions, of course, is what we would call the trivial solution. It's that there's not a wave, but that's kind of boring. So instead, let's imagine here, let's combine some of these equations together. What I'm going to do is I'm going to take some of these things and I'm going to take one of these derivatives and I'm going to plug it into another one of the derivatives. And I'm going to end up with these two expressions right here. These two expressions right here are telling me the second space derivative of the electric field is equal to E naught mu naught second time derivative of the E field. And we actually find the exact same thing with the magnetic field as well. If we go through and plug in the exact same equations as we've got with these things, we would find the same deal. Well, in that case, let me not think about del as much. Let me just remember that del is x, y, and z. Let me focus on x. If E is changing with x, and that's equal to some constant times the second time derivative, this is our old wave equation. This is our old wave equation for sine waves, for regular oscillatory motion. This is how light propagates. And not only that, but this constant term right here is the velocity of the wave squared. So you can try this right now. Go ahead and take your calculator, plug in 1 over square root of E naught times mu naught, and you'll get back the speed of light, the speed of electromagnetic waves. This is really one of the massive things that I think was very understated about Maxwell's equations, is that understanding the speed of light, this was the groundwork for determining relativity, right? This is what Einstein used to really justify coming up with the theory of relativity. And then later evidence showed that this was how the universe actually worked, but he needed this particular piece to make that happen in the first place. Now, this results in sinusoidal waves, right? Sine waves. And if you are thinking about traveling electromagnetic waves or the traveling of light, this is the most common picture you'll find, right? The idea here is that the electric field, as it changes, induces a magnetic field. The magnetic field, as it changes, induces an electric field, and they constantly induce each other, and they propagate forever. The fun part of this is, and the part that I don't have written anywhere else, is that this is not the only solution that we can have. So the electric and magnetic fields can indeed point like this, but they can also be offset by a quarter of a wavelength. And offsetting them by a quarter of a wavelength is not something commonly seen, but it's known as circular polarization. So most of the polarization of light we know is linear. It's like this. It's either vertical or horizontal. I think I've talked about this before, but how your sunglasses have a certain polarization to them. They only allow light of one way to go through. You can have other solutions to these, though. And in fact, there was something, I think it was in the 80s, that they actually found another solution to Maxwell's equations. They were plugging in all the conditions and everything else, and they found another solution to Maxwell's equations, another way that light can propagate. And it's a very uncommon way, but it's supposed to be a non-diverging solution. Because naturally, laser light will slowly diverge over time, but this was supposed to be a non-diverging solution, and it's really fascinating. There are multiple solutions to these equations, though. There are multiple different ways that light can propagate through the universe. And it's an incredibly fascinating thing, how it works. Because light's everything, right? Light is so much as we use it nowadays. Optics is in every single field. But I think that's it. That's all I've got. That's the end of the semester. I am going to continue making a couple more lectures over some of the really cool things that I do want to show you guys, but they are not going to be any part of the course at this point. This is the end of the course. The extra lectures are purely just because, man, they're really cool. And I think some of you guys will really get a kick out of it. But this is it. This is the last of the material to be covered officially in the course. I really do want to thank you guys for being here, for participating, for everything. It has been a real pleasure to do the semester, the year, through all of the madness and everything else. I appreciate every single one of you guys that has stuck through it. I can't say that enough. Thank you very much.